Next, I'm now pleased to welcome Professor Dawn Song, a professor in computer science at UC Berkeley and co-director of the Berkeley Center on Responsible Decentralized Intelligence. Her research focuses on AI safety and security, and she is ranked the most highly cited scholar in computer security. She is the recipient of numerous awards, including the MacArthur Fellowship, Guggenheim Fellowship, and more than 10 Test of Time awards and Best Paper awards. Dawn, it's a pleasure to have you here in Shanghai with us. I'll let you take it from here.
Great. Thanks, everyone, for being here. Yes, my name is Dawn Song. I'm a professor at UC Berkeley. Today, I'll talk about AI safety challenges and future directions. So the presentations earlier have set great context and background. And here, I wanted to add some more emphasis. In particular, as we deploy machine learning, it's really important to consider the presence of attackers for a number of reasons. So first, history has shown that attackers always follow the footsteps of new technology development, or sometimes even leads it. And also, this time, the stake is even higher with AI. As AI controls more and more systems, attackers will have higher and higher incentives to compromise the systems. And also, as AI becomes more and more capable, the consequence of misuse by attackers will also become more and more severe. And hence, it's really important to consider the presence of attackers, especially as we consider AI safety. So first, I want to talk a little more about AI safety in the presence of attackers. From my group's earlier work and also other research work, we have shown that adversarial attacks are prevalent in deep learning systems. Essentially, all deep learning systems today, they are all vulnerable to different types of adversarial attacks. And the number of papers in this space actually has grown exponentially since our earlier work and the people's earlier work in the early stages. And also, we had the rare honor of having some of the artifacts of our earlier work actually now is part of the permanent collection at the Science Museum of London. So as we talk about safety, and today talk about safety-aligned large language models, it's also important to consider the adversarial setting. So unfortunately, as our work and also others' work have shown that these large language models are also really vulnerable to adversarial attacks, and these safety alignment mechanisms are easily broken. So in our recent work, as an example, Decoding Trust, which provides the first comprehensive evaluation framework for trustworthiness of large language models, it's actually won the Outstanding Paper Award at NeurIPS this past December. We developed new algorithms and also different environments, including benign adversarial environments, to evaluate many different perspectives for safety and trustworthiness of large language models. And our work has shown that for all these different perspectives, including adversarial robustness, toxicity, and fairness, and many others, essentially these large language models are all very easily attacked by adversarial attacks. And again, for more details, you can go look at our paper at decodingtrust.github.io. And also, these adversarial attacks are effective on multi-model models as well. And also, others' work have shown that even as these models are being fine-tuned, attackers actually, by providing just a few very small number of adversarial designed data points, this fine-tuned stage can essentially cause this fine-tuned model to easily lose the safety alignment. So far I've talked about, right, so these attacks, they are not only effective at inference time, they are also effective at essentially fine-tuned stage, as I just mentioned. Essentially, this is called data poisoning as well. And also, through this data poisoning step, also, these models can have what we call very stealthy behavior, where essentially called backdoor as well. So in our earlier work, we showed that through data poisoning, the model attackers can build in backdoor in the model such that, for example, in our earlier work in facial recognition, the model under normal circumstances will just behave normally and give correct facial recognition results. But however, when anyone that wears a special type of glasses, and this actually is even effective, in the physical world, then it will cause the model to essentially trigger this backdoor that the model will misrecognize this person wearing this particular type of glasses to a targeted, as a targeted person. And through recent work with, by Anthropic, they have also shown this type of backdoor phenomenon where a fine-tuned large language model during normal circumstance with a normal prompt, it can generate like normal code, that's usually correct code. But when a particular trigger phrase appears in the prompt, the model actually will generate a vulnerable code. So all these are different types of adversarial attacks. In the entire community, we have been very productive and creative in coming up with different types of new attack methods. However, on the other hand, unfortunately, in the defense side, we have seen very little progress. And today, there's no effective general adversarial defense. So this illustrates that this is the first open challenge that I wanted to pose in the context of AI safety. And the current AI safety alignment mechanisms are very easily evaded by adversarial attacks. And any effective AI safety mechanisms need to be resilient against these adversarial attacks. And hence, this poses a huge open challenge. So essentially, in order to achieve AI safety, we need to actually be able to solve adversarial robustness as a prerequisite. And as I just mentioned, despite that now we have thousands of papers every year publishing on different types of adversarial attacks, but the entire community essentially have made almost zero progress in defenses against these adversarial attacks. So for developing effective AI safety as a whole community, we really need to push forward in how we can develop better defenses so that we can develop AI safety mechanisms that are resilient against adversarial attacks. So what are the potential directions that can help us to achieve this goal? So here I'll give a couple examples from some of our recent work. So one work is what we call representation engineering. And this is a top-down approach to AI transparency. So in this case, we, by providing the model with contrastic inputs as a stimulus for certain tasks, so we provide these contrastic inputs to the model, and then we monitor the activation of the neural networks at different layers, and then build the models. And with our recent work, we show that through this method, we can actually identify certain directions along at certain layers that actually correlates with different classes, different types of behaviors of the model. So essentially, for example, we can identify certain directions that actually correlates with behaviors, whether the model is honest or not honest, whether it's hallucinating or not hallucinating, and so on. And furthermore, our work with the collaborators and so on, we have also shown that this type of method called representation control. So not only that we can do representation reading, which is to monitor the model's behavior, we can actually modify the activations of these neurons at certain layers during the inference time. along, for example, the identified directions and so on. And then through this way, we can actually then change the model behavior for certain classes. For example, using this method, we can make the model behaving more honest or less honest, and so on. So why is this important? I think this is one of the key distinction actually between human brains and artificial brains, artificial neural networks, is that for these artificial neural networks, we actually are in control in the sense that we can completely observe the activities, the activations of the neural networks, and also in real time, we can modify the activations of the neural networks. So this actually gives us a powerful arsenal for potentially for AI safety. So this allows us to observe and monitor the behaviors of the neural networks, and then provide better control and enforcement of the behaviors of the neural networks. So hence, this can be a really promising direction for providing AI safety control mechanisms. However, this type of control mechanism is promising, but it's difficult to actually give full guarantees. So also as Professor Yaqin and also Joshua mentioned earlier, ideally we actually want to have provable guarantees. So recently we have a joint initiative on quantitative AI safety. And the goal is to actually develop AI safety that's with guaranteed, essentially, with safe by design, with guarantees for safety. This actually is also in parallel and in some sense inspired by the approach taken in cybersecurity. So including my own work in the last 25 years in cybersecurity, we have moved, essentially we have had paradigm shifts in how we approach safety, how we actually build secure systems. Early on, the whole community focused on reactive defense, how we detect attacks, and so it's kind of like how we detect when large language models is behaving wrong. And then later on, we worked on methods as a proactive defense, but focused on bug finding, essentially try to find vulnerabilities in these systems. So it's kind of like today we are doing these evaluations, we are trying to find some kind of vulnerabilities in these large language models and so on. But however, these approaches are unsatisfactory for a number of reasons that I don't have time to get into. And in the end, the community realized that the best approach for achieving security is what we call secure by design or secure by construction. So with this type of approach, essentially, we can develop systems that provide a provable guarantee of its security, that it satisfies certain security properties by the design and the construction of the system. And this is in contrast to the other types of defenses that I mentioned earlier, which helps us to essentially get out of the cat and mouse game and also provides provable guarantees. And the method used in this is through formal verification. So with formal verification, first we provide formal specification of desired properties, and then through formal verification, we can then formally verify that the system is secure satisfies the desired properties through verification. And this also can be done at different levels, including the design level and the implementation level. And in fact, in the past decade, the community actually has entered into what I call the era of formally verified systems, where we actually have many different types of systems, including microkernels and file systems and compilers and so on, and that are formally verified. However, the issue for these systems is that it's extremely labor-intensive to prove these systems, the security property of the systems. Each one often takes tens of proof engineer years. So it's not scalable. My group, in collaboration With others at OpenAI, we were among the first to use deep learning for theorem proving. And this work was done quite a few years back, way before large language models and so on. So today, with the large language models technologies, we hope that we can take this work even further, where we can, instead of training in the past, for example, training AI agents to play Go, we can instead train AI agents to automatically prove theorems and verify programs. With this approach, in conjunction with program synthesis, which my group also has done a lot of work in the past, was among the pioneers in the space as well. And we hope that by combining these approaches with automatic theorem proving for program verification and program synthesis, we can provide automatically provably secure code, producing code with proofs attached to it. And with this approach, we can use AI to build provably secure systems, essentially achieve secure by design or safe by design. And this can help us to reduce arms race to provide provably secure systems that are resilient against certain classes of attacks. So this approach, I think, is extremely promising to solve certain classes of problems. But however, it still has a number of open challenges. First, this type of formal verification approach mainly applies to traditional symbolic programs. But it can be difficult to apply to non-symbolic programs, such as deep neural networks, where we don't even have precisely specified properties and goals. So for example, if I want to guarantee that a self-driving car doesn't drive over a pedestrian, we don't even have a formal specification of what a pedestrian is. And also, in the future, essentially all systems, most of the systems, will be hybrids. They will be combining symbolic and non-symbolic components. So formal verification and secure by construction, how can we apply this approach to this type of hybrid systems? It's still a big open question. So to conclude, as we all discuss and agree here, AI safety is extremely important. As we move forward with stronger capabilities of AI, it's paramount, it's of paramount importance that we guarantee the safety of these systems. But however, there are still many challenges. It's important to consider AI safety in adversarial setting, and I think it can be very productive to develop methods using activation, steering, representation control to build as an important arsenal for controlling model behaviors. And also, finally, we hope that we can really develop new approaches and mechanisms to enable secure by design and safe by design for building secure AI systems with provable guarantees. Thank you.
Thank you so much, Dawn. Please stay on stage as we transition to our panel.